blood coming in a pulmonary capillary. Now, we know this has just come, or this has come from the body, right? So we're assuming it would be lower in oxygen, if that makes sense, and higher in CO2. So if we were to actually look at the values coming in, we can measure them. In venous blood, the partial pressure of oxygen at rest is about 40 millimeters of mercury. That means of the total pressure of gases in blood plasma, the amount due to oxygen is about 40 millimeters of mercury. That means that it's more or less oxygen in venous blood than in alveolar air. Less, right? 40 millimeters of mercury here due to its concentration, 100 there. CO2, if we were to measure that, it's about 46 at rest in venous blood. So now we come in this pulmonary capillary, and across the membrane, there is a gradient for the two gases. There is a higher amount of oxygen here and a lower amount of oxygen here. There's a higher amount of CO2 in the blood than there is in the air, so it will move out. So that's why gas exchange occurs. Now, what do you know about diffusion? Is it proportional to a concentration gradient? Yeah. But are these two, is the concentration gradient the same for oxygen as it is for CO2? No. So you would expect more oxygen to diffuse, right? Except it doesn't. Remember this? What's that? Cellular respiration. I have to, is there a difference in the volume of oxygen and CO2 that get exchanged, or the concentrations that get exchanged? No, they're equal, right? Okay. So even though these pressures are different, the amount of gas that diffuses is the same. And the reason for that is because of their solubility in water especially, and in the membrane. Oxygen, not very soluble in water whatsoever, so more difficult to diffuse. Carbon dioxide is pretty soluble in water, so it's easier to diffuse. So you got a difference in pressure here between 100 and 40, right? That's the pressure gradient there. And you got a difference in pressure gradient here between 46 and 40. Yet the same amount of gas is diffused because the solubilities are different. Oxygen's harder to diffuse because it's less soluble, so it takes a steeper gradient. CO2 is more soluble, easier to diffuse, so it takes less of a gradient there. So don't be confused by the fact that the gradients are different. We know that equal volumes of gases have to get exchanged because of what happens in cellular respiration. But the reason that it's equal volumes is because of their solubilities being different. Not a big deal, but that is true. Now, air is constantly moving in and out of the alveoli, right? Blood is constantly flowing through a pulmonary capillary. There is no ability to reach a stable equilibrium between the two because they're always moving. In fact, air is always being refreshed at 100, blood is always coming in at 40, so there's always this pull, if you will, of oxygen into the bloodstream. There's always this pull of CO2 out. So what really happens is that the equilibrium happens at these levels because the air is constantly being replenished. So if we look at blood coming out of a pulmonary capillary bed, its oxygen level is going to be what this is right here. If we look at CO2 coming out of a pulmonary capillary bed, its concentration is going to be what it is right there. Because we're constantly pulling in, it's called counter current. We're constantly pulling in one direction this way, and another direction that way, so we're really driving the diffusion of these gases. So now if we look at arterial blood, what are the partial pressures of arterial blood? Well, oxygen is 100 millimeters of mercury. Why? Because that's what it was right here. What's it going to be as you move further away from sea level? This number goes down. There's less oxygen, so this number goes down. Right? So that's why you have less oxygen when you're up at high altitudes, is because there's less oxygen in the air. There's less total pressure. So because there's less total pressure, this number's less as well. You okay with that? So now my arterial blood gases here, now this is going out to the tissues, are going to be oxygen rich and CO2 poor. Now they go to the body's tissues. Now the cells are constantly doing this. So because cells are constantly doing cellular respiration, oxygen levels are always low, CO2 levels are always high. At rest, how much oxygen is there? It's not totally zero, there's some, and it's about 40 millimeters of mercury oxygen. So that's about how much oxygen is present in interstitial fluid. CO2, about 46. Again, this is at rest. Obviously, the more active the tissue is, the oxygen goes down and the CO2 goes up. But at rest, it's these numbers. So again, what's happening? As soon as oxygen comes out, cells are using it. Right? Blood's constantly moving through, CO2 is constantly being produced, so we never reach equilibrium here. So these are the values we get now when we come over here. So now, because we can't reach equilibrium here, blood coming out this way is going to be oxygen poor, the same as the interstitial fluid was, and CO2 rich, the same there. And so now we're back to 40 to 46, and we're back where we started. So there is a gradient here. Sometimes we call this external gas exchange, or external respiration, because it occurs between blood and the air from the external environment. Sometimes we call this internal gas exchange or internal respiration because it occurs between blood and the internal organs. So we have these gas exchange at these two places, and because of that pressure gradient being present. Now this is what it should be at rest. Under normal conditions, it should do this. Now, you're okay with that? Is that okay?